Well, hi there, Nick here, M0NTV, and welcome back to my shack and to, yes, another homebrew video and to another video about mixers slash modulators. And in particular, we're going to be looking today at something I've not really covered properly before, which is how do we match the diodes in our diode ring mixer. And spoiler alert, I've built a little circuit which I'm quite pleased with really, and I'm hoping is going to make my life a lot easier and hopefully your life a lot easier as well if you want to roll your own diode ring mixers. So I hope you find something of interest here. So why bother matching our diodes anyway is a fair question to start with. So we've got our diode ring schematic there on the right hand side, and you think, well, you know, why don't you just grab 4 diodes? And in my case, I use 1N5711 small signal Schottky diodes. They have a fast switching action and a low forward voltage drop, so they're very good, and they're not too expensive, especially if you buy them in bulk, and we'll get onto that a bit later. But why not just grab 4 diodes, solder them together like that, and say jobs are good, right? Well, part of the reason why that might not work too well is tied in with what the diodes actually do in our diode ring. Now, I'm not going to go into this in too much detail, and there's lots of very good explanations of how a diode ring mixer actually works, but I just want to show you just what these diodes do from the point of view of the local oscillator. So if you imagine we've got our local oscillator signal connected here and here, what actually happens is this. Now let's say that we're going to feed our diode ring with a sine wave, and I covered this last time. I know the purists will say no, you need to feed it with a square wave because it'll turn the diodes on more quickly. Yes, it will. But by the very nature of feeding it with a square wave, you're also feeding your mixer with a whole truckload of harmonics that are going to mix with everything else in there as well. So, you know, there's no such thing as a free lunch, is there? So on balance, I'm going for a sine wave. Now, imagine here's the zero line here. Imagine on the positive excursion of our local oscillator, what happens is this port looks positive, and this port looks negative. That looks like the ground. So what happens is that current will flow through these 2 diodes that are in red, and the grey bit looks like it doesn't exist. It's out of circuit because it's reverse polarized. So when the signal goes positive, what you get are these 2 diodes switching on. And then what happens is when the signal goes negative on the next bit of the wave down here, and you see what's happened, the polarity is reversed. So on the negative excursion of the sine wave, now this looks more positive and this looks negative, and these 2 diodes that were switched on are now switched off, and these 2 that were off are now on, right? So what you're actually doing with our diode ring is we're turning on and off 2 diodes at a time at the frequency of the local oscillator signal. So pretty fast, right? And where the mixing magic happens, of course, is as this is happening, we're also, if it's a modulator, feeding an audio signal in there to give us our modulated output signal, or if it's a mixer, we're feeding another RF signal in there to give us, well, either an audio signal if it's a product detector, or another RF signal. But from the point of view of the local oscillator, all we're doing really is we're switching on 2 diodes, then we're switching them off, and then we're switching on these 2 diodes, and then we're switching them off. So if you think about it, these diodes are just acting as switches, and the way they do that, of course, is because they have a forward voltage drop. But they're all different. Even the same kind of diodes, as I said, we're using 1N5711, they'll all have a slightly different forward voltage drop. But when you think about it, the signal needs to overcome that forward voltage drop to properly switch the diode on, and so that the current can flow. And you really want both your diodes switching on and off at the same time. But if they've both got different forward voltage drops, and over here as well, they're going to be switching on and off at different times, and that will negatively affect the efficiency of your mixer. So that's why we need to match these diodes, and what we're matching are their forward voltage drops. We want diodes that will drop as far as possible the same amount of voltage, so that when they switch on, they'll switch on together, and when they switch off, they'll switch off together. So that's, in a nutshell, really why we match our diodes. So, how can we match our diodes? Well, you could say, well, this is easy, isn't it? I just grab my multimeter. Every multimeter I've ever seen has got a diode function on it, and yeah, just use that. And indeed, you can use that, and if you've got nothing else, then it's clearly better than nothing. But the issue with using your diode function on your digital multimeter is just this. It uses a fixed current, but it's a very low current, usually much less than a milliamp, which it uses to test that diode. And the problem is that you might be able to match your diode. If you've got a whole load of diodes, you might be able to match them and get them matched really well. But if you're matching them at a current level, which is much less than a milliamp, but then you're going to use them at a current level which is much more than that, there's no guarantee that just because they were matched at that low current level, they will be matched at a higher current level. And let me just prove this to you with this next slide. So what you're looking at here now, all right, full confession, I've got one of those flash DCA Pro Peak Atlas instruments. That's an advanced semiconductor analyzer. It's a little handheld thing, but it's a really cool little device, and you can test diodes and transistors and MOSFETs and lots of things, and you can plug it into your computer and do these fancy graphs. Now what this is doing, just so you can see, and this is the familiar IV diode curve. So you've got the current going up the y-axis, and you've got the voltage going on the bottom on the x-axis. Now, what I did is I grabbed 10 randomly selected 1N5711 Schottky diodes from a big bag of them. So they weren't matched, they were just 10 random ones. And I tested them with my little device and produced these nice graphs. And what it actually does, it just tests each diode at different current levels and measures the forward voltage drop. And but I want to draw your attention to two things. So this red line here, so this is the 1 milliamp line. So now if you look here at how all our diodes initially, they're turned off completely here, then they start to turn on. And at 1 milliamp, they're all bunched up together. So I mean, you know, you could grab these same 10 diodes and test them at 1 milliamp and think, well, actually, they're all pretty well matched, really. I mean, there's hardly anything between them at all. But look, as the current level increases, how these curves spread out, and there is clear daylight between some of those traces. So if, for instance, we were going to use these diodes in our double balance mixer at, say, 10 milliamps, now that's a whole different kettle of fish, because, and these are the same diodes, the same diodes that look pretty well matched at 1 milliamp don't look very well matched at all at 10, and that is the issue with measuring at a very low current level, but then using them at a much higher one. So that's why we need a better way, I would suggest, of actually matching our diodes. And so we need to match them at the current level that we're going to drive them at. which brings me to the next question really of what should that be? And as you know, I always have to stress, I am not an expert in any of this, and rightly or wrongly, this was how I arrived at my decision. And so my rough and ready calculation went like this. If you think about, you'd normally feed a diode ring mixer with 7 dBm of local oscillator signal into a 50 ohm load. Now 7 dBm equates to about 5 milliwatts of power, which is 1.416 volts peak to peak. So this means 0.5 volts RMS. And as Mr. Ohm tells us, the current equals the voltage over the resistance, so that's 0.5 volts RMS divided by 50 ohms is 10 milliamps. So I'm figuring we really need to be able to test our diodes at about 10 milliamps, read their forward voltage drop, and then match them accordingly. And even if we're not using them actually at quite that level, you'll see, if you could match them at a higher level when they're all more spread out, you've got a far better chance of them being matched at a lower level when they're all more bunched together. So I think testing at a higher current level is probably quite a good idea. Right, so what's a better way of doing it? Well, a tried and trusted method is what I would call the simple current controlled test circuit. Now the diagram on the right hand side comes from Alan Wolke W2AEW, and Alan has a brilliant video where he covers this same material, but Alan does know what he's doing. He is an expert, so you need to listen to Alan. And he uses this method which others have done it. Charlie Morris, ZL2 CTM, has used it before, and indeed I've used it myself, and it works. Of course it works. If Alan and Charlie are going to do it, of course it's going to work. But what it involves using 2 digital multimeters. One we have in circuit here as an ammeter to read the current, and one we're using the voltage setting of, not the diode setting, the voltage setting across your diode to read the forward voltage drop. And it relies on having some variability either in the voltage that you're feeding the circuit, or in the resistance, because what we need to do is vary one or the other of that so we can vary the current. Because what happens is you stick your diode in here, and let's say we were measuring we were testing at 5 milliamps, let's say. So you then adjust, and what I did is I had a fixed resistor, and then I just varied the DC voltage on my bench power supply so that the ammeter reads 5 milliamps as close as possible. And then what happens is you take that one out. So you read the forward voltage drop. Once you've set that to 5, you read the forward voltage drop. You take that one out. Then you put the next one in. But you can't just read it off because they've got different forward voltage drops, these diodes. I mean, that's the whole point of the exercise, isn't it? But that will affect the current going through the circuit. So if you were to just put it in and read it out, you wouldn't be testing it at the same current level as you tested the other one. So what that means is you have to keep tweaking, in my case, the voltage to get the ammeter back to read precisely 5 milliamps, if that's what you were testing it at. And so you're constantly taking a diode out, you're putting one in, and you're tweaking this, and then you go too far and you go back. And to be honest, I just found it a bit fiddly, and it took ages. It works, but it just kind of left me thinking, surely there must be a simpler way of doing this. What we really need is a circuit which the current will remain stable and constant in, even when we swap the diodes in and out. So what we need I decided was a constant current source. And a constant current source, of course, is unlike a constant voltage source. Most of my experience, and I guess a lot of you watching this video, your experience will be with a constant voltage source. That's like your battery. That's like your desktop power supply. You know, if you dial in 12 volts on it, you want 12 volts there, irrespective of what the load you put on. If you want 12, you want 12 volts. So, but a constant current source does the opposite, if you like. Well, not the opposite, but it's not bothered about the voltage, it's the current. So it ensures that a fixed amount of current is passing through the circuit, irrespective of what the load is. And actually, this is a fascinating rabbit warren to disappear down for a few weeks, which I did, actually. And so I investigated current sources and sinks, and that really just depends on where it is in the circuit. Current mirrors. It's fascinating. Really, really interesting. Just general kind of electronic stuff. And so I did quite a lot of research. I did quite a lot of building, and I built several different constant current sources. But there were two that I particularly liked, and the one that I've gone for is probably the simplest one, and is the one that I'm going to show to you now. That is this. Now, I call this the M0NTV adjustable constant current source for diode matching, but, you know, folks, this is not original to me. It might have my call sign up there, but I've done very little tinkering to this basic circuit. As a matter of fact, this circuit, well, let me just explain. It uses an LM317, which is an adjustable voltage regulator, a little 3-pin device. And they're easy to come by, they're not too expensive, and usually they're used for adjustable voltage. But actually, in the data sheet of the LM317 is a circuit which is almost identical to this, which is for a constant current source. And essentially what happens is you vary this potentiometer here, which will enable you to dial in a different current. But then, irrespective of your load, and in our case the load is this diode under test here, you will get that fixed amount of current going through. And in a few moments, when I show you what I've built, we're actually going to test this and you'll see for yourself. Now what I did is I actually put in a 51 ohm resistor here, so that the current is limited, and actually by having the 51 ohm resistor in here and having this 1K linear potentiometer, it means I can go from just over 1 milliamp to just under 25 milliamps, and you can set the current level at anything in between those levels. And the great thing is once you've set the current, you can swap the diode in and out and the current won't change. And so, you know, and in actual fact, as you'll see in a moment, you can really mess around with the load under test, and the current won't change. It's really quite bulletproof, this circuit, so I'm quite pleased with it. Now, things that you need to watch out for. Now, you can dispense with both of these, the resistor and the potentiometer, and just put in one 120 ohm resistor, and that will give you a fixed current of 10.4 milliamps, thereabouts. And you could do that if that's all you're going to use it for, but I thought if I'm going to build this thing, it'd be good to have some variability so I can test things at some different current levels. What you need to watch out for, now I'm running this at 5 volts, that's about as low as you can go, because the LM317 needs some headroom. It needs 3 volts across it, and we need 1.2 0.25 volts across the resistors, which leaves very little really, just that's going to fall on the load. Now, if you're testing low voltage drop, small signal diodes like I am, that's fine. If you're going to test things which will draw more current, you'll probably need to up the voltage, and that's fine as well, because you can just up the voltage and that'll just give you more current there, and it will just give you more headroom and make sure that your current stays where you want it to stay. So you could use it to test, LEDs or something that are going to draw more current. So that's fine. But for my purposes, I found that for testing these 1M5711s, I could run it at 5 volts and it was all happy. Right. Okay. Well, let's have a little look then at it. And it didn't get a bit more simple than that, does it, really? You can't see the little capacitor. So we've got a little capacitor, 100 nanofarad capacitor there. Well, it's going to ground, and actually that's just going to ground from the 5 volt. That's just to stop any kind of ripple on the power supply, actually. So you can't see that, but it's buried behind here. But, I mean, that's all it is. It's a capacitor, a resistor, potentiometer, LM317, and then a couple of probes for our diode. And that's what I built, and it works very well. But I didn't obviously want to keep it like that, having breadboarded it and found out that it worked. I wanted something that was going to be as easy as possible, and just putting the diodes on like that with those little clips, I thought, well, it's not too bad, but it might be a little bit fiddly. So I thought I could try something else. So this is what I actually ended up doing, and so you'll see this is the basic schematic you've just seen with some other circuitry here. Now all this is a double pole, double throw switch with a couple of points for my multimeter probes. So that's what the P plus and the P minus is. It's just the black, the red and the black leads of your digital multimeter. That's where they're going to go. And obviously the D plus and the D minus are the anode and the cathode for your diode. And I've put the wiring in here. So essentially it just means when your switch is up, you're in current mode. Which means you can, it just means these same two, I can use the same two binding posts really for my multimeter probes, whether I'm measuring the current or the voltage drop. I can just use the same two, so that just made life a bit easier. You'll have to obviously swap the leads on the multimeter if your multimeter's like mine, but you don't need to have separate probes when you're measuring current and voltage, which is useful. So when the switch is up, basically what you're doing is having the multimeter as an ammeter in series in the circuit, and you're measuring the current. So you do that then, so you switch it up and you use the potentiometer to set the current to where you want it. Then you swap your multimeter probe over, so you're back to voltage, flick the switch down. Now you're measuring the voltage drop over the diode. And then all you have to do is, when you've measured that one, take it out, put the next one in, measure it, and it's as simple as that. So that's the basic gist, and I'll put a link to these, to all these schematics and diagrams in the video description below. And this is what it looks like. I'll show you the real thing in just a moment, but this is essentially what it looks like in the little enclosure that I built it in. So here's the LM317 up here. So just be careful with the pin out of the LM317, because it looks like a standard kind of voltage regulator, but we're used to kind of a kind of an in and out and a ground, but it's not like that. You've got an in and an out and adjust, and they're not as they appear to be here either. So just make sure you check the data sheet and get the pin out right. But that's it. Really very simple. practical little circuit. So let me show you the thing itself as it is now, and then we'll test it, and then we'll actually do some diode testing. And so here is what I actually built. So it went into this little plastic enclosure. So you see we've got the power 5 volts coming in there. We've got the multimeter probes. They just slot loosely in there. That's fine. That's the potentiometer to control the current. And we've got our switch here. So it's up for current and down for voltage. And then those same little binding posts, then you can just unscrew those a bit and just drop your diodes in the little gap there and just tighten them just slightly so they make enough contact. And yeah, that's where your diodes go. And so if we just turn it around, you'll see it should look familiar because it's just like I showed you on that little piece of paper. So there's our switch here, which does the necessary switching. You can see the capacitor up there and the resistor hanging off the potentiometer. And yeah, so really very simple. But let's put it on and I'll show you how it works. Okay, so here we go. So I've got just a random selection of some 1N5711 Schottky diodes here, and I'm just going to put them in and we'll see. So first of all, just to show how bulletproof this is, let's just put one in. So we're set to current at the minute. And so you see we're measuring here 10.08 milliamps. And okay, take that out, put another one in. .08 milliamps. .08. Now normally using the two multimeter method, you'd be having to tweak that current to get it to stay at 10.08 milliamps. And as I said, it will go from 1 up to just under 25. 10.08 milliamps. Now, okay, let me mess around here. This is a 200 ohm resistor. 10.08 milliamps, right? Okay, and if you really want to mess about, what did I do with that lead? Hang on a minute. Let's find one here. Okay. I'm going to short it to ground. So no load at all. 10.08 milliamps. That's pretty impervious to changes in the load. That is precisely what we want. Now, just to show you all of these measured 10.08 milliamps current, which is great. So we're testing them all at the same current. This is what they actually look like in the measurement mode. So we're up in current now. So what we're going to do now is we're simply going to change the multimeter to voltage. Click it into voltage. Now we're going to put these on there. Okay, so now we're measuring the forward voltage drop. 0.755. Get rid of that resistor.
0.724. So a bit of difference. 0.770. So these are the same diodes that we measured an identical current through. 0.755, 56. You need to give it just a couple of seconds to stabilize. This is a very good multimeter. .777. So what you would do is that, and you can see how quick it is, really. I mean, you could probably just get away with dropping them in a bit more easily than that once you get going. But how easy it is to actually put the diodes in, read the forward voltage, and what you would then do is get a big sheet of paper and write down the totals, so you're gonna have some idea of where you're gonna be, and there'll be some odd ones you'll have to put on a separate sheet of paper, but you'll find they'll clump into groups around certain values, and so you put them on that by their value, and then you'll end up, if you get a load as I did, so I got 100. I got, I think, from, I don't know, Banggood or AliExpress or somewhere, and I would do that. So I would just go through every one and do that, and I'll end up with big sheets of paper all on the desk over there, and hopefully I have some clumps then of diodes which are all forward voltage matched, and then you can go about then picking ones then that you're going to use. And what I would suggest is that once you've done this work, is that you do match them, and you match them for future use as well. So you match them into groups of 4, because it's generally going to be 4 that you're going to be using. And then when you come to actually building a diode ring, you can pull out 4 you've already matched, because you've done the work in advance. So there it is, and I think that's going to save me some time and trouble, and hopefully it will do the same for you as well.
Just to say, you don't need to test the current through every single diode as I did. I was just showing you that we did indeed have a constant current going through there, so you don't really need to do it once, and then you can just read off the forward voltage. The subject of this video is actually an article that I have submitted. Matter of fact, the first article I've ever submitted to SPRAT, which is the quarterly magazine of the GQRP Club. So if you subscribe to that, you'll probably read that article there. If you don't, I would highly advise that you join the GQRP Club. It's fantastic value for money, and SPRAT is just a tremendous little magazine with all kinds of homebrew ideas. So it's very well worth checking that out. And I think probably we'll have one more video on just wrapping up mixers, because I don't know about you, but I'm just about mixed to death now. I need to go and build some other things. But anyway, I hope you found that of some interest, and it's a simple little device really, but hopefully should give us some more accurate results, and be a little bit easier to use as well. So thank you ever so much for watching, and any questions or comments, just stick them down below. If you haven't subscribed, please do, and I will see you on the next video. But until then, look after yourself, take care, bye bye, 73.